Welcome back to my channel. In this video, we're gonna discuss about the two-sum problem. I won't just show the answer, but I will show the actual thinking process that takes us from the brute force to the optimal solution. Let's quickly see the problem statement that we are given an integer array nums along with an integer target. And we have to return the indices of two numbers such that they add up to the target. And it is sure that there is exactly one solution exists and we have to return that, and we are not allowed to use the same element twice. Let's quickly go through an example. We are given an array nums and also a target 9, and we have to check whether there exists two elements. We have to return the indices of those two elements such that their sum should be equal to the 9. And here if we see that 2 plus 7, which is equal to the target 9, we have to return the respective indices of 2 and 7, which is 0 and 1, and this will be our output. And what is the most straightforward way to do this? Let's say we are having this array, and let's change the target to some other value, which is somewhat 26. Now I stand it here, and I gonna see all these remaining elements and want to know whether there exists of some elements such that it sums up to this current element, which will be equivalent to the target. Not got it? No problem. Okay, now I gonna check, like linearly I have to check, right? The most straightforward way is to check the linear way, and I start from here. 2 plus 7, which is 9, no, not equal to the target, move forward. 2 plus 11, which is equal to 13, not equal to target, move forward. 2 plus 15, which is 17, not equal to the target, therefore it's done with 2. I'm gonna change my element and I'm gonna move forward. Now 7, I'm gonna check the remaining elements. Got it? Now 7 plus 11, 18, not equal to target. 7 plus 15, 22, not equal to target. Done with 7. I'm gonna move forward. I'm at 11. I'm gonna check the remaining element. 11 plus 15, 26, equal to the target, therefore return the respective indices, which is 11 index is 2 and 15 index is 3. This will be my output, and let's quickly code this up. I'm gonna travel from 0 to n minus 1, where n is the length of the array, and I'm gonna take the another pointer j, which generally goes from the next index I plus 1 to the last. And if I found anything that makes sense, like if nums of I plus nums of j, which is equal to the target, then I have got those numbers, right? Then I have to return the respected indices I comma j. Got it? This will be our solution. And let's quickly analyze the time complexity and space complexity for this approach. This for loop takes a time complexity of order of n. This loop also takes a time complexity of order of n, right? And this checking, it takes order of n. Returning also takes order of n. And if we see the overall time complexity, we have a nested order of n, which will result in order of n cross n, which is nearly order of n square. And the space complexity is, as we are not using any external data structure to store any elements, it stays constant. Got it? But let's look at the constants here. The maximum length that the nums can take is 10 power 4, and our time complexity order of n square. Let's put this in it, which is order of 10 power of 8. We can do 10 power of 8 operations. This code will work, but the interviewer will be not happy with this code because he needs us to optimize this further. So, and the most disadvantage thing that we are facing in this approach is that we are revisiting elements multiple times. Like for 2, I am revisiting 11 sorry 7, 11, 15. Again for 7 also I am revisiting all this, and for 11 I am revisiting this 15. Yeah, I'm doing a repeated task for multiple times. So in order to skip this, I need a data structure which stores the elements that I have been traveled so far. Like I need a data structure which gives me or which tells me whether there's a presence of an element in somewhat less time complexity, or nearly I can say that it should take nearly or approximately order of n time complexity. And yeah, we have one beautiful data structure called set or hash map, which gives me a approximately order of one lookup. Like it tells me whether there's a present of an element or not in just order of one time complexity. Got it? And yeah, let's simulate this here. And target is 9. Initially the hash map is empty, right? Therefore I'm standard here. What I require, like the target is 9 and I currently am at 2. The required is 7. Does 7 present in the hash map? No, it doesn't. Therefore I'm gonna move forward. But before moving to the forward, I'm gonna make sure that this element should be marked. Therefore the key is the element itself and the value is the respected index, which is 0. Which is 0. And let's move to the another index, and I'm standing at 7. The required will be 9 minus 7, which is 2. Yeah, does 2 present in the hash map? Yes, it does. Therefore we have to return the respected value of that required number. Here we require is 2 and the respected value for 2 in the hash map is 0, comma the current index of 7, which is 1. Yeah, done. Therefore let's take another example with the target 18. Now I'm standing at here. The required or the needed will be target minus the current. 18 minus 2, which is 16. Yeah, that's 16 present in the hash map? No. Therefore we will move forward. But before moving to forward, we have to note it down into the hash map with the respected value, which is the index 0. Therefore, yeah. Now 18 minus 7, which will be 11. Does 11 present in the hash map? No. Move forward. But before moving to forward, we have to note it down in the hash map, which is the respective index 1, right? And 11, for 11 the required will be 18 minus 11, which is 7. Yeah, the 7 present in the hash map? Yeah, it does present. Therefore the respective key of that needed will be 1, because yeah, this is the one. The value of that respective needed will be present in the hash map, which is 1, and comma the current index of 11, which is 0, 1, 2. Yeah, this will be my output, and we have to return this. And let's quickly code it up. For I, which takes from 0 to n minus 1, and if I have to calculate the needed will be the target minus the current element, which is nums of I. If needed in hash map, I have to return the value, right? I have to return the value of that respected needed. Therefore return hash map of needed, which indirectly gives me the respected index of that needed and I. And if there is not presence of needed in the hash map, then I have to make sure that I also hash map of that respected nums of I have to store it in hash map, right, which will be equal to I. Like the value is the index itself. And let's quickly analyze the time complexity for this approach. This loop takes a time complexity of order of n, takes order of 1 present in a, this is the interesting thing about hash maps. It gives approximately order of 1 time complexity to look up, like it checks whether a needed is present in the hash map or not in approximately order of 1 time complexity. And it's also order of 1 nearly, it's also order of 1 nearly, which will give me the entire time complexity as order of n cross something, order of n, that's it. And the space complexity for this approach is, as we are using one external data structure, sorry, I have to initialize here the hash map, and the space complexity for this approach is order of n, because at 15 we have been seeing so many elements like 2, 7, 11. This is order of n minus 1, right? Nearly around order of n. When we find the element at the last, like if the target is something around like 17, then in this case at 15 the required will be 17 minus 15, which is 2. We're gonna require the entire elements to be stored in the data structure. Got it? Therefore the space complexity for this approach is order of n, and the time complexity for this approach is order of n, and this is the most optimal time complexity and space complexity for solving two-sum problem. Thank you, and I'll see you in the next video.